Okay, good morning. So, last Friday we finished the chapter 5, and we know that we have the problem and we apply the continuity equation to the problem to understand the velocity field. And as we know, the basic idea for the chapter 5, we are focused on the mass conservation for our velocity, uh, for our flow environment. So the chapter 6, we move to another topic and we change the physical properties mass to the momentums. So for these chapters, as we know, our target is the momentums. So how significant difference compared to the continuity equations? So the slide shows the key concept as the sentence I show in here. As we know, the momentums of the flow particle in the control volumes is corresponding to the external force and over the momentum flux curls through the control surface. Okay, so we know that this is the idea similar to the continuity equations. So, and we have the two environments similar to the continuity problems. So the first is we still have the control volumes and we still have the control surface, but now we didn't discuss the mass exchange along the control surface or the mass change in control volume with the time difference. Right now we move the mass to the momentums. Okay, and another topic for this chapter is the differential form of the momentum equations. As you remember, in the final slide for the chapter 5, I introduced the continuities differential form, and based on the differential form of the continuity equations, we can tell you some stories related to the velocity field. And we also introduced the string function and the potential function to describe the string lines for our velocity flow field. But for in this chapter, the final, I will also teach you the differential form for the momentum equations, and this is very important. We call that is the control equations for the flow velocity field. Okay, so because we discussed the momentum changes, so we know that if we have the momentum m, and if the momentum change with the time will equal to the external force. This is our external force. So what is, we call that the external force. That means sum of the force is not balanced. So means the sum of the force is not equal to 0. So we have some external force. And the external force is equal to the momentum change with the time. So the key target for this chapter is the force first. After we understand how to make the force balance, and we know that we have the external force, and we can go back to discuss with the momentum change with the time. So as you see, the slide show the list of the this topic of learning outcomes. The first one, we focus on the Newton's second law. We know that based on the Newton's second law of the motion, we know that F equal to mass multiplied accelerations. And if the force balance and then sum of the force equal to 0, so we know that the particle may has the motion with the constant velocity. And then after we understand how to make the force balance and we have the external force, so we move to the next. We have the linear momentum equations will be introduced, and the final part we change the linear to angular momentum equations. And the difference compared to the chapter 5 is under the momentum equation chapters, our control volumes will be moved. So how to take into account for our problem when the control volume is moving. So we need to know how to process the problem with the moving control volumes. Okay, so go back to the Newton's first law and tell us that the sum of the force mass balance means the sum of the force is equal to 0. And in that condition, we know that the particle will move at constant speed. Okay, so and for the force, we can divide it to two different types. The first is the body, the second is the surface force. So how different it is. But before we introduce the difference and the comparison between the body and the surface force, we know this that we have one target is airplane. And for the airplanes, how many force we have? We know the first is normal is the weight. We will have the weight, right? So it's caused by the gravity. And we have some jack force is contributed from the air. Then we have a thrust force to push the airplane forward, go forward. And we have some lifting force. Okay, so totally we know that we have the flow force for the target of the airplane. And as we would like to know what is the body and what is the surface force. So this slide provided certain definitions for the body and the surface force. So it's easy to have a certain definition because the surface force is a force that requires the physical contact or touching between the two interacting bodies. But the body force is the force that can act without physical contact. So go back to our problem for the airplane. We exactly know that the weight is the body force because the weight is contributed by the Earth's gravity. Okay, so there's no contact between the airplane and the Earth. But some surface force, such as the drag force, lift force, thrust force, the force will act with the surface of airplane. So we call that is the surface force. So this is a slide summarize all the force we meet. So we don't need to discuss more for the body force because, for example, there are the force normal in our life, like the magnetic force, is electric force, and the gravity force. But the right-hand side summarizes all the surface force in our environment. For the fluids, we have the pressure force, shear force, and the buoyant force, lift force, drag force, surface tension force, and thrust force. But for the solids, we have a frictional force, tension, applied force, spring, support force. So for fluid, we will know for the pressure, the shear force is from the viscous effect. The buoyant force we are discussed in the chapter related to the static fluid. And the lift and drag, we didn't introduce more details, and the thrust and the tension force also. So in the following class, we will meet some forces such as the lift and the drag and the thrust. And in that way, I will introduce more details about such the force shown here. Okay, so and then we move to the Newton's second law. Okay, so as I mentioned, if sum of the force is not equal to 0, we call that the external force for our systems. And then external force is equal to the mass particle multiply the acceleration. So if we go back to see the airplane problems, actually we have the accelerations normal to the path. So the dashed line showing the path for airplane, we actually know that we have the acceleration normal to the path. So if we go back to the force balance, so you see we have the lift force. This is airplane with the inclined angles uh, compared to the vertical lines with depicted with the theta here. So if we try to make the force balance, we know that the lift force can convert to horizontal and the vertical force, and the vertical force need to balance with the weight. But the horizontal force, there is no any other force to balance with the horizontal force induced by the lift. So that we will have the external force along the x direction. We call that the AN is the acceleration normal to the path. So that's the summarize what we need to do. So the textbook that propose a methods, we call that the visual solution methods. So the idea is we divided the process scheme the for our problems. So that we have the step 1, step 2, and step 3. So first, step 1, identify the vector equation in its general form. So This is our general form, just based on the Newton's second law. And the second, we draw a diagram to understand what the problem we meet. So we draw the diagrams and finally solve the problem with the force balance, and we convert the vector force to a different project to a different horizontal x and y vertical direction y, and we can make the force balance for each component. As I mentioned, we have the lift force, and we take the sine theta and which convert to the force project on the x directions. Okay, so this is a force balance along the x directions. So we have actually external force related to the acceleration normal to the path. But for the y direction, it's different because the weight is downward, but we have this force project to the first vertical component to make the balance. So totally we don't have any external force. Sum of the force along the y directions is equal to 0. Okay, so this is a similar ideas. What we would like to do when we meet the problems, we just follow the visual solution method with the 3 steps. So we need to the general formulas first, and the step to sketch the diagrams, and finally we write the balance force equation. Okay, so as I mentioned in the first slide, we have the external force, and the external force is equal to the mass multiply the accelerations. So, and we also tell you the momentum change with the time is equal to external force. So we know what is the momentum. We have the momentum m is equal to the mass multiply the velocity. So we have the velocity and we have the mass, and we take the differential with the time should be equal to external force. Okay, but so we know that the external force equal to dmv dt, and the general problems we meet, the mass of the particle must be constant. So we know we can take the mass outside, and the inside in the differential only dv dt is equal to accelerations. Okay, and usually we are consider there are many particles in our system. So how does the momentum change it? We need to take the sum sigma, sum of the total momentums for each particles. Okay, and we know we focus on our problem for the closed systems. So actually the external force is equal to the momentum changes with the time in our closed systems. So go back to the nano transport theories. We know the nano transport theory tells us the extensive properties change with the time in the closed systems is equal to the intensive multiply the low dV integrate, and this is the properties in the control volumes change with the time. And for the control volumes, we always to see that is the cumulate or that is uh, some physical property flow out. And this is we are focused on the exchanges along the control surface for our physical properties is the intensive property multiplied the low V dot product with the small cross-section area. Okay, so and we know that we defined the intensive is equal to the extensive divided the mass. Okay, so for the chapter 5, we tell you the intensive, but we are focused the physical property is the mass. So in that way, the intensive B is 1. But right now for our chapter 6, our topic for the extensive property B is the momentum. So if we put the B for the momentum here, we know actually that is the mv. So we divided the mass of the mv, so B will change to the V velocity. So right now, for the go back to the Reynolds transpose series, we replace the capital B by the momentum m, and we replace the in small b intensive property by the velocity v in here. So please notice that this is our linear momentum equations, but the two parameters they have the same physical unit. The small v factor is we call that the velocity, but the capital V here is also the velocity. But they are the velocity group, but why we use the different V? The one is small and another one is capital. Let's write down some definition here. The small v is the vector and is the fluid velocity relatively to an inertial reference frame. But the capital V is also the vector, but is the velocity relative to control surface. So this is meanings. This is relative to the control surface. So if this is our system, and there are some flow coming, this is the inflow. But as we know, this is the control surface boundary for T1 time, but maybe the control surface will moving. This indicates the control volumes changes with the time to the next time step. So if we have the same velocity in here, so there are some relatively velocity because the control surface also move with the time. Okay, so the relative velocity v to the control surface will change if our control volume will change also with the time. So, and if we move the linear momentum equation to the next, we know that the momentum change in the closed system is equal to the external force. So this is our formulas, final formula for the linear momentum equation. That means the external force is equal to the momentum changes with the time in control volumes, and the momentum flux curves through the control surface. And in that way, we have the inflow momentum flux and we have the outflow momentum flux, and we make the balance. Okay, so and this slide just point out the ideas if we consider that each particle inside the control volume have the same velocities. Okay, so for this is formulas, we can take the velocity outside because it didn't change in the control volumes. So we can summarize our final formula is the dmcv multiplied bcv dt, and we don't have any integration operator because the velocity is constant in the control volumes. And for the control surface, we assume the velocity is the uniformly velocities. So we also can take the velocity outside, and then the inside is the momentum, is the mass rate for the inflow and the outflow. So finally, we can also remove the integration operators and replace the integration operator by the sigma operator here. And we have the outflow and we have the inflow and then make the balance, so there is the minus. Okay, so this is our another form for the linear momentum equations. Just replace the integrate operators by the sigma sum operator here. Okay, I think for the chapter 6, today I just introduced briefly. So on the Friday this week, and we will do some exercise, try to understand well, and try to understand what is the basic concept for the linear momentum equations. Okay, and as you can image that our problem may corresponding to the force, and we have the system force balance, and then discuss how change it for the momentum. OK， 好，那现在开始我们来讲解一下今天的考试的题目。OK， 那上次已经有说明，就是在小考的这个部分，各位有这个上传作业的这个难处。那希望大家都已经熟悉如何去切换成这个影像档，然后做上传的这个动作。那我们这一次如果你迟交，我们就是一概不受理，因为我希望这个礼拜大家已经非常熟悉如何去上传这个作业。好，那第一个问题，这个是在我们上个礼拜在最后的这个几个 slide， 那我们想告诉你，其实我们在定义这个 string function， 我们在定义这个流线函数的时候，这个 perc 这个符号，其实可以写成它的定义是在 u 方向的这个流速其实会等于这个 perc 在 y 的方向上的微分区 minus， 那在 y 方向的流速其实会等于 perc 在 x 方向的微分。那这是什么意思？代表我们现在这个 perc 是我们的流线函数。流线函数在它的这个梯度的这个流线函数在y 方向的变化，我们定义它其实是 x 方向的速度场。那在 x 方向上的变化，我们定义它为这个 y 方向的这个速度场。那这个是一个很重要的定义在流体力学里面因为我们如果知道速度 U 跟 V，其实我们就可以去定义它的流线长怎么样子。那大家知道速度就是流线的这个梯度的方向。好，那我们来看一下，这个 stream function 在这个 flow 的条件下，它的流场可以表达成流场的这个可以表达成 v 其等于2x 在 i 方向上，然后负的2y在 j 的方向上。所以其实你知道这个问题的 u 跟 v， 那请问它的 stream function per c 会等于什么？所以大家可以去做做看，这是一个积分的问题。那记得积分出来要保留一些参数项，要做一个讨论。好，那这就是我们的题目1。那题目2，题目很短。第一个是我们有什么条件？他说这个 pipe 会有一个束缩的现象，就是左下角这个问题，从左边到右边的管子其实是变直径是变小的。那他说这个有个测压压力计测到这两个有一个测压这个水头的这个差距是0.3米，是0.3米。那请你决定在这个流场里面的流量是多少？那他没有要你算出数字，因为他只给你压力的差距，高差是0.3米。那在跟你讲，在这个大的断面里面的这个直径是0.1米，那在小的这个断面的直径是大 D 来表示。那请问你在这个流场里面的流量是多少？叫你用描述流场，用 D 的函数来描述。那所以大家可以去想一下这个问题要怎么解决。我们有教过哪些方程式可以告诉你做一个平衡？那我们有伯努利方程，也有连续方程。那你怎么来思考这个问题 ？OK， 好，那现在我们就开始考试。那大家记得就是这些答案然后题目都要写清楚，然后并拍照也要清楚，这样助教才方便去做更改。OK， 那等一下考试考到9:50，那时间快到，我会跟各位提醒一下。务必在写完以后一定要上传清楚的这个影像档。好，开始。 哦，刚才抱歉，同学，那个第二题的图在这里。那因为本来图也没什么太多的这个资讯，我现在在更正在这里，还有大概7分钟，各位同学还是可以继续作答。好，各位同学还有3分钟哦。 好，同学，我们时间到了，哎，要交作业了。好，那记得大家礼拜五再继续上课。